We want to develop this equation called the ideal gas law, PV equals nRT, and what we specifically want to do here is to figure out this gas constant called R. So that's what we're looking at right now. Now, looking back a little bit, we know that we have several variables: pressure, volume, temperature, and the number of moles. We've been looking at these two at a time. So first off, we said Boyle's law is pressure times volume is a constant, and that is constant if the temperature and the number of moles stays constant. So this constant that we're getting is not really a very constant constant. It's only constant for one problem because it depends on the temperature and number of moles. When we get to Charles' law, okay, here we have the volume divided by the temperature, and again the temperature is in Kelvin, that's a constant, but again that's only constant if the pressure, okay, and the number of moles stays constant. So this would work for, say, like a balloon. Now, Gay-Lussac's law, we saw in the video, same deal. Okay, it has a constant, but again, that constant is only constant if the volume and the number of moles stays constant. So that was like in the movie where they had the glass container that couldn't change its volume. Finally, here we have the combined gas law, and the combined gas law, pressure times volume over temperature is a constant as long as the number of moles stays constant. So in each of these cases, okay, the constant is not really a very constant constant because it depends on one of these variables. Make sure that that stays constant. Well, if we get all four variables involved, then we have what we call the ideal gas law. And we can see we have pressure and volume over number of moles and temperature. And those four things, if we put those in these conditions, we get a constant. And this constant really is a constant constant. So this constant is going to be true, we would call it a universal constant. And the symbol for that is R. And I think of that because, this is the real constant. Whether that's the real value, why it's R, probably not, but that's what I always think about. So this constant is called R. So we see this as P times V over N times T is R, and that's not really the way people write it. We saw on the first page, people say PV equals nRT. Move the N and the T over here, so we get PV equals nRT. Now, all the other kind of laws before were sort of before and after laws. Okay, you had a can, gets run over by a truck. Okay, so now the volume has decreased, and we could say, well, what happens to the pressure inside? Or if the volume is decreased, what happens to the temperature? Or what happens to both the volume and temperature? But it's always a before and after, P1, V1, T1, P1, P2, T1, T2, V1, V2, that kind of a thing. But for the ideal gas law, then what we have, let me clear this up a little bit. Okay, what we have is one situation. So let's say now we had a 2-liter bottle, so we know that that's our volume. And let's say it's nice outside, it's 25 degrees Celsius, which we immediately change to 298 Kelvin. Okay, let's say that we know that the air pressure today is, let's say, 0.95 atmospheres. So we know the volume, we know the pressure, we know the temperature. So how many moles of gas would fit inside this 2-liter bottle? So this is not a before and after situation, it's just one situation. And so sometimes this gas law is also called the equation of state. Because it just has to do with, one state of the substance at this time. That's really hard to read. Okay, but ideal gas law or equation of state. Well, what we want to do now is figure out, well, what is the value of that constant? If it's a constant constant, then we need a number for that. So what we're going to do is go back and say PV over NT is equal to a constant R, and all we need is a situation where we happen to know the pressure, the volume, the number of moles, and the temperature all at the same time, and then we can calculate a value of R. And it turns out that we have that just hanging in the room there. We know that 1 mole of a gas has a volume of 22.4 liters. Add STP, Now STP, you might remember that standard temperature and pressure. Standard temperature is 0 degrees Celsius, which will immediately change to 273 Kelvin. And standard pressure is 1 atmosphere pressure, or that could be 760 millimeters of mercury, or 101.3 kPa. Now, because there are different pressures that we could use for our value, we actually get a couple of different values of R, and those values, they all work the same, but they actually have different numbers. So let's just throw these first ones in. So for this beach ball, so let's go ahead and put in some values for pressure, volume, number of moles, and temperature, and calculate a value of R. So let's say we say pressure, let's say the pressure is 1 atmosphere, and we know that the volume of this beach ball is 22.4 liters, and we know the number of moles we're talking about is 1 mole. And finally, the temperature, that is 273 Kelvin, because of course we're working in Kelvin. And you know that's going to be good, because if you put in 0 degrees Celsius down here, you can't divide by 0. Now, if you put those 4 values in, then what you end up with is 0.0821, and you can get more significant figures if you want, liters, atmospheres per mole, Kelvin. Now, those units are amazing looking, because whenever you have a constant, it has to have units that cancel out all the other units in the problem. So all we need here then is, if I want to do a problem, then I can say R is equal to 0.0821 liter atmospheres per mole Kelvin. If I wanted to do this with 760 millimeters of mercury, we would do the same thing. We would change this number, and it's still R, and it's still just as useful, but we're going to get a different value. In fact, we get 62.4 liters millimeters of mercury, or torr, per mole Kelvin. Now, if we do it again and say we want to use 101.3 kPas, we can do the same thing, and in that case we end up with a value of 8.31 liters kPas per mole Kelvin. Now, on the actual AP test, okay, they have the equation. They give you these values here for the constant. So here we can see the number we just had, 8.31. Okay, liters kPas, that actually turns into joules, okay, mole Kelvin. Or we have 0.0821 liter atmospheres per mole Kelvin, or we have 62.4 liters torr per mole Kelvin. So these values are actually given on the exam, and what we've introduced here is the ideal gas law. It's a very useful law, and all you have to do is go through and you can say pressure, volume, number of moles, R, and T. Now, the last part of this is you can take this equation and change it around a little bit. Okay, if you want to do something like figure out the molar mass of something, well, we know molar mass is moles per liter. And we can see that moles is N, that part, and the volume is liters, so V. So if you take PV equals nRT and solve for N over V, then that is actually the molar mass. So molar mass would be N over V, which is going to be, I have a little hard time with this. Okay, I think that's going to be P over RT. You better verify that, because I'm just doing this on my head. But you can calculate the molar mass of something. In the same way, let's say we wanted to do density. Okay, density is mass per volume, dmV. Okay, so mass, we have moles. Okay, moles, we can get mass divided by molar mass, and divided by the volume. Okay, so you can wish this around again and figure out the density of a substance, especially of a gas. So you can get gas density by playing with N and V. Okay, we can get molarity, okay, I said this wrong back. I said molarity. I was thinking molar mass, and so this is wrong. you need to go back and calculate it. But the idea is you can use this equation to figure out molar mass and to figure out density. Good luck.